Good morning and welcome to MAE 106, Discrete Mathematics with Probability. My name is Richard Kohar and this is Lecture 13. And in today's lecture we'll be covering Venn diagrams and the principle of inclusion and exclusion. So in our previous lecture we had covered Venn diagrams, and we'll just do a couple more examples, two to be exact, and we'll introduce the principle of inclusion-exclusion, as easy as pie. Just a reminder that on Friday we have our test 1. It'll be done over Zoom. You can see the details through Moodle. You'll be expected to scan your solutions. You can use things like your phone, a scanner app. Don't really care which one. A suggestion could be like Dropbox. Or if you actually used, or if you have a scanner that can scan pages quickly. The camera is really out of focus. It might be that your resolution has downgraded. So just in the corner of your screen, just click the little gear. It's something like this, right? And it should boost the resolution. I hit F5. We're good now. Okay. So you can scan your solutions. It doesn't matter to me how you convert it, but you'll need to convert this to a single PDF. Yes, you can scan using notes. There's a limit of 20 megabytes. And the additional comment is that you'll be allowed one 8.5 by 11 sheet of paper. For a cheat sheet. Okay, but nothing else. For help. No textbooks. No friends, etc. What if your printer doesn't work? What if the printer doesn't work? Well, then you will just write out the question on a piece of paper. No printer. No problem. You'll just write out. You will look at the questions. On screen. And write your answers on a separate page. Yes, that's okay for printing and scanning if it's in another room. we don't have access to a printer or scanner, can we use a tablet to edit the To make it fair for everyone, please just use paper. No tablets, please. Just because the way that we've done it is that you'll have a webcam and you will have a look. The idea is that so we can see that you're writing. When we do a proof for the test, do we have to say, or do we just write it out? You don't have to. The rule of inference. Okay. Okay. So hopefully that answers those questions. Again, just look on Moodle and you'll see the extensive, sorry, not extensive, but the more details. And there's a little picture of like how your setup should look. So, and then there's a practice link to try uploading a PDF file. Okay. So let's do some examples. So we're going to do 2 examples. We're going to do Venn diagrams. And this one we're going to use with unions. So here's our example. And we're asked to do shade in the A union B, union C prime. Okay. It's not allowed to write. You don't have to write them out, but it helps. Again, you're trying to convince me that you know what you're doing, and it's about communication, and it won't hurt if you write down which rule that you're using. I hope that answers the question. Okay. So we're asked to shade this in, and I think I'll use something like a pencil maybe. So the nice thing with shading in with unions is that we can just keep adding on to it. So again, we have A union B, so I can just shade this in. Here's A union B. Okay. So A union B. And then we have union C prime. So it's everything outside of C. So it's everything outside of it. So this would include the A, B. So it's everything kind of outside that. So we get to shade in more. We can be careful to not shade in things that we don't mean to. so that in the end, the only thing that we don't shade in is in there. Okay. Let's move on to the second example. We have something with intersections. What about the stuff that overlaps? A, B, and C. That stays shaded. Yes. Because with the or, it can be in A or B or not in C. Yes. So that's the thing with unions. It just kind of keeps, we can keep filling it in, we can keep adding it in. But with the intersections, that can be a little bit harder for people to visualize sometimes. So let's do A intersect B intersect C prime. And I'm going to do two of them. So again, 3 sets. Okay, so in this case, what we want is the intersection of A and B. So that's right in here. So I'm going to use one directions here. And then what I want is I have to intersect everything outside of C. So everything outside of C, I'm going to use different. Making sure that I'm not going through C. So what that leaves us with is just this spot right here where it's hatched, it's cross-hatched. So I have just in that round area there. So that's where it overlaps. So it's just right in through here. Okay. Now, there's another way that you could do it as well. So what we could do is we could label these regions 1, 2, and 3, 4, 5, 6, oops, 7, and 8. Okay. Okay, where did I use this? So for set A, this would have regions 1, 2, 4, and 5. B here would have regions 1, 3, 4, and 6. C would be 1, 2, 3, 7. And of course, our universal set that we have that we're working with is 1, 2, 3, all the way up to 8. Okay, so then what we would do then is we would say, okay, A intersect B. We look for where we have same where there's the same elements or the same regions. So 1 and 1, not 2, 4, and that's it. So just 1 and 4. Okay. Which makes sense, 1 and 4, so that's right there. Then the other one that we can do is we're going to do take that and let's do C prime. So that would be everything outside of C. So not 1, 2, 3, 7, but 4, 5, 6, and 8. And then what I'll do is I'll look for overlapping sections from the A intersect B with C prime. And in this case, the only number that I see, not 1, because 1's not in here, but 4. So and again, that corresponds to region 4 here, so that's the only one, so that's what we would fill in. And that's it. So there's two ways of doing it. You can use kind of like the crisscrossing lines, or you could write it out using regions. So that's just two different ways of doing it. Okay. So now we can go on to the principle of inclusion-exclusion. Okay, so what we're going to do draw a Venn diagram here. Okay. Okay, so what I'm going to do is I'm going to create a Venn diagram. And I'm going to say I have 3, I have 4 in here. I'll say I have 5 and 6 here. And then 7, 8, 9, and 10. So, here's a question for the class. How many elements are in A? Yes, 4. Good. Then how many elements are in B? Yeah. Number of elements in B, 6, okay. 1, 2, 3, 4, 5, 6, good. So, if we were thinking about this as a counting problem, some people might say, okay, I have the number of the set in A and I have the number in the set in B. So that's 4 plus 6, which gives me 10. So the question that somebody might ask, you know, if they were curious, is if I add the number of elements in A and the number of elements in B, is that equal to the number of elements in A union B? And what does everyone think? No. Yes, I'm going to say not necessarily. Okay, so in this case, so in our case, in this case, let's say we can count the number of elements in A union B, which is this shaded region in here. So there's 1, 2, 3, 4, 5, 6, 7, 8. Okay. So, which is not equal to 10, which was what we said was when we added up A plus the number of elements in A and the number of elements in B. Okay. So, what is the formula? for A union B. Well, what we could do is we notice that there's just a difference of 2. And that difference of 2 comes from the overlapping 2 elements that are in between A and B. So that's what we can actually do, is if we instead subtract the intersection, subtract 2 would get us to the 8. So that's what we can do. That is then the formula for it. So what we'll do is we'll add up the 2 sets. Okay, and we've overcounted, so we'll subtract what we've overcounted, which is the intersection. So in this case, we would get 4 plus 6 minus 2, which gives us the 8. Now sometimes we might not be able to write out all the elements in here. So as a quick way of writing this, some people will write it like this. They would just put the number of the elements are in that region. So in this case, I have 2 elements. They would put 2 here. In this one, they would put 2 here. And there is 4 as well. So again, you can quickly add up those regions. 2 plus 2 is 4, plus 4 is 8. Notice that I said not necessarily is the number of elements in A plus the number of elements in B equal to A union B. And I said not necessarily. Can you think of 2 sets where this would be true? If there's no overlap, or yes, exactly. So that's, you know, it would be equal to this if the intersection is equal to 0. So this is kind of the formula. So I'll write this out. This is the kind of make a summary of what we've found. So this is the principle of inclusion, exclusion for 2 sets. And that's the number in the union A for 2 sets equal to the number in A, the number in B, number of elements, subtract the number of elements in the intersection. Be careful I don't just make one big smear. Okay. So that's the formula for 2 sets. So if we have no elements, which means that the intersection is empty, this means that A and B are mutually exclusive. And by that, I mean something like that, where there's no overlap. Exactly. Okay, so if I have the universal set is 100, I have A is 70, B is 60, and the intersection is 50. Okay. So starting with this, we can use our principle of inclusion-exclusion. So again, we have the number of elements in A, the number of elements in B, minus the overlap. So that means that I have 70 plus 60 minus 50, which gives me 80. What we'll do now is I'll draw a Venn diagram. Okay. So again, I can write out what I have here. I have my intersection is 50. There is 70 in total for A. So I'm going to do 70 minus 50, which gives me 20. For that region. And over on the B side here, I have a total of 60 minus 50, which gives me 10. And then outside of all of this, I know that the universal set contains 100. So I know that I have 20 plus 50, that's 70, plus another 10, that's 80, which means that I have 100 minus 80, which equals 20. So here's 20. But really what I've just done there was I took the universal set right? I took the universal set, the number of total that I had, and I subtracted 20 plus 50 plus 100, but that was what we had, which was 80, but that is the union of it, the A union B. So and this makes sense because this is everything outside of the union. So it's the total of the universal set, which was 100, minus 80, which gives us 20. So now that we had pi for 2 sets, here's pi for 3 sets. So when we had pi for 2 sets, it was equal to the sum of the individuals cardinality, or that's the number of elements, right? The cardinality the individual sets A and B minus the cardinality of the two-way, or just the intersection. And this is how we're going to extend then for 3 sets. So if I have 3 sets, it's the sum of the cardinality of the individual sets so that would be A, B, C minus the cardinalities of the two-way intersections plus the cardinalities of the three-way intersection. Okay, so you're thinking three-way intersection. Yep. So when we get to this, So you'll have the 1, 2, 3. You have 3 two-way intersections, so they're overlapping with the A and C, A and B and C. And then you have the one right in here where it intersects the three-way between A, B, and C. So what you would end up doing is you would remove the intersection between A and B and C, and what you've ended up doing is kind of remove too much. You have to add back in now this intersection. So algebraically, this is equal to the individual sets. So you have A plus B plus C. Then we subtract the two-way intersections. So A intersect B minus A intersect C minus, and then B intersect C. And then we add in the three-way intersection. So A intersect B intersect C. Which leads us to an example. Let's do an example. Oh, and I'll leave up the formula. There we go. I'll put it up at the top there. Okay, so we were told that there was 120 students who have cars, and they're asked about their car stereo system, and 46 said that they had XM radio. 52 said that they had a CD player. It's those plasticky things that we burned music onto. There's 50 students that have a USB port. 25 students said that they had XM and USB. "21 said that they had XM. Oops, sorry. Had a CD, and the other one had a USB. 23 said that they had a CD and a USB. And lastly, 16 had all of them. So they had XM, CD, and a USB. So you can have a question that says something like, okay, how many of these students have at least one of these options? The XM, the CD, or the USB. So what we can do is it's basically asking us what is the number of the union of all these? So they're kind of asking, what's XM union CD union USB? And the nice thing is we got the formula for this, and it tells us, again, we just add up all the individual ones, which we have here, XM, CD, and USB. We subtract the overlaps, the two-way overlaps. So we'll subtract 25, 21, and 23. And then we add in, finally, that three-way intersection. So doesn't there need to be a none category for it not to be 120, the total? I think you're getting ahead of me. We can do that next, because the next part would be how many have none of those options? Okay, because we can do that. Remember what we did last time? We just would do the complement of this. So we'll get to that question next. But all we have to do is we'll add up the individual ones. So it's 46 plus 52 plus 50. We subtract the individual, or the two-way. So minus 25, minus 21, minus 23, and we add in 16. Okay. And you should get 95. So that's the other question. How many have none of these options? Again, what that is asking is the complement of that. Okay, so we were told in total there's 120 students that were surveyed. At least one of them, 95 of them have one option. So then that's where you can use this piece of information, the 120, and you subtract the 95 from that to get 25 students have none of those. Okay, the other thing to announce before I head out, again, we have the test on Friday. If you have questions, feel free to send me an email. Thursday at, let's say, 7 p.m. I'll have an hour of office hours. Okay, just to handle any questions, this will be done over Zoom. Can you go up a little to 8? Yes, I can. There we go. Okay. there's not any more questions, I'll sign off for today. Thank you everyone for tuning in, and I hope you enjoy the rest of the afternoon. Take care.